The Unseen World, an introduction to quantum physics. Welcome to a journey through the unseen, the mysterious, and the infinitely small. Today, we are delving into quantum physics, a field of science that has baffled and amazed scientists for more than a century. Quantum physics is the study of matter and energy on the smallest scales, scales that are much, much smaller than even atoms. We're talking about particles like electrons, protons, and the mysterious photons of light. The world of quantum physics is different from the one we experience every day. Here, particles can behave like waves, objects can be in multiple places at once, and the concept of reality as we know it becomes a shifting puzzle. It's as if the rules that govern our everyday world no longer apply when we look at the very fabric of the universe. To understand quantum physics, we must first step back to the early 20th century, a time when scientists like Max Planck and Albert Einstein began to notice that classical physics, the physics developed by Isaac Newton in the 17th century, was no longer sufficient to explain certain phenomena. Classical physics works wonderfully well at large scales. Think of planets orbiting the sun, or even objects as small as grains of sand. But when we zoom in, when we look at particles smaller than atoms, classical physics falls apart. One of the first mysteries that classical physics couldn't solve was the nature of light. At the beginning of the 20th century, physicists like Max Planck realized that light didn't behave like a simple wave, as had been thought for hundreds of years. Instead, it seemed to come in small, discrete packets of energy. Planck called these packets quanta, and this idea laid the foundation for quantum theory. In 1905, Einstein took this concept further with his explanation of the photoelectric effect, an experiment that showed light could eject electrons from a metal surface. To explain this, Einstein proposed that light was made up of particles, which we now call photons. This was one of the first major breakthroughs in quantum theory, and it won Einstein the Nobel Prize in 1921. But light wasn't the only thing behaving strangely. Electrons, the tiny particles that orbit the nucleus of an atom, also began to reveal their dual nature. Louis de Broglie, a French physicist, suggested that electrons, and all matter for that matter, could behave like both particles and waves. This was a revolutionary idea at the time, and it set the stage for some of the most mind-boggling discoveries in science. To better understand this, let's conduct a thought experiment. Imagine you are standing on the shore of a calm lake, tossing stones into the water. As each stone hits the surface, it creates ripples that spread out in concentric circles. This is what we typically associate with waves. Now imagine that instead of a stone, you toss an electron into the lake. You'd expect the electron to behave like a tiny marble, moving in a straight line, right? Well, in the quantum world, that electron behaves more like the ripples than the marble. It spreads out, behaving like a wave, and yet it is still a particle. This wave-particle duality is one of the central mysteries of quantum mechanics. This brings us to the famous double-slit experiment, one of the most important experiments in the history of quantum physics. First conducted by Thomas Young in 1801 to demonstrate the wave nature of light, the experiment was later adapted for quantum particles, like electrons. When scientists fired electrons through two slits, they expected them to behave like tiny bullets and create two bright spots on the screen behind the slits. Instead, the electrons created an interference pattern, as if they were waves passing through both slits simultaneously. Even stranger, when scientists tried to observe which slit the electrons were passing through, the interference pattern disappeared and the electrons behaved like particles again. This experiment revealed something profound about the nature of reality. The act of observation seems to change the outcome. In the quantum world, particles don't have definite positions or velocities until they are measured. This concept is known as the observer effect, and it raises deep questions about the nature of consciousness and reality itself. Are we influencing the universe simply by observing it? As we journey deeper into the quantum realm, we will encounter more of these mysteries, from quantum superposition, where particles can exist in multiple states at once, to quantum entanglement, where particles remain connected across vast distances, influencing each other instantaneously. Quantum physics teaches us that the universe is not as solid and predictable as we once thought. Instead, it is a place of infinite possibilities, where the very act of measurement brings reality into being. In the next chapter, we will dive into one of the most famous and perplexing thought experiments in quantum mechanics, Schrödinger's cat, and explore how quantum superposition challenges our understanding of reality. Schrödinger's cat, a paradox of quantum superposition. Welcome to one of the most famous thought experiments in the world of quantum physics, Schrödinger's cat. It's a name that even those unfamiliar with physics may have heard, often used as a metaphor for things that seem contradictory or ambiguous. But what exactly is Schrödinger's cat, and why is it so important in quantum mechanics? Let's set the scene. In 1935, Austrian physicist Erwin Schrödinger devised this thought experiment to highlight the peculiar and paradoxical nature of quantum superposition. The experiment involves a cat, a sealed box, and a rather unusual setup. Inside the box is a Geiger counter, a small amount of radioactive material, a vial of poison, and a hammer. The radioactive material is set up in such a way that within the span of an hour, there is a 50-50 chance that one of its atoms will decay. If the atom decays, the Geiger counter detects the radiation, the hammer is triggered, and it breaks the vial of poison, killing the cat. However, if no decay occurs, the cat remains alive. According to quantum mechanics, before we open the box and observe the system, the radioactive atom exists in a superposition of two states, decayed and not decayed. This means that the cat, too, is in a superposition of being both alive and dead, at least until we observe it. The act of observation collapses this superposition into one of two definite states. The cat is either alive or dead. But before that observation, the cat is in a strange limbo, both alive and dead at the same time. This paradox is not meant to suggest that cats, or any living beings, can actually exist in such a superposition in the real world. Rather, Schrödinger's cat was designed to show just how strange quantum mechanics is when applied to the macroscopic world. In the quantum realm, particles can indeed exist in superposition. They can be in multiple places or states at once. But when we try to apply this concept to larger objects, like cats, it leads to a paradox. So what does Schrödinger's cat really tell us about quantum physics? It reveals a fundamental tension between how we perceive the world at large scales and how nature behaves at the smallest scales. In our everyday experience, objects exist in definite states. Your phone is either on the table or in your hand, not both. But in the quantum world, particles like electrons and photons don't follow such simple rules. They can be in multiple places or multiple states until we measure them. This brings us to the concept of quantum superposition. In the quantum world, particles exist in all possible states simultaneously until they are observed. It's as if every possible outcome is happening at once, but only one becomes real when we measure it. Imagine a spinning coin hovering in the air in a state of both heads and tails. It's only when you catch the coin and look at it that it becomes definitively heads or tails. That hovering state of both possibilities, that's quantum superposition. The implications of this are profound. In the realm of quantum mechanics, particles like electrons can exist in superpositions of multiple energy levels or positions. A photon can be in two places at once, or an atom can exist in two different energy states at the same time. But why does this happen? One of the great mysteries of quantum mechanics is that we don't fully know why nature behaves this way. We know that quantum superposition occurs, and we can even observe its effects in experiments, but the deeper reason behind it remains elusive. Now, let's take a deeper dive into the science behind quantum superposition. This principle plays a key role in the famous double-slit experiment we mentioned earlier. When particles like electrons are fired at a screen through two slits, they create an interference pattern as if each particle is passing through both slits simultaneously, a hallmark of quantum superposition. However, if we attempt to measure which slit the electron passes through, the superposition collapses and the particle behaves like a solid object passing through only one slit. It's as if the act of observation forces the universe to choose a definite outcome. But how does this work on a mathematical level? The state of a quantum system, such as an electron or a photon, is described by a mathematical entity called a wave function. This wave function contains all the possible states of the system, all the potential positions, energies, or spins that the particle can take. As long as we don't observe the system, the wave function remains in a superposition, encompassing all these possibilities. However, when we measure the system, the wave function collapses into a single state. This process is one of the great mysteries of quantum mechanics. It's known as wave function collapse, and it challenges our classical intuition about how the universe works. Schrödinger's cat is a playful yet profound illustration of this concept. It forces us to confront the strange and counterintuitive reality of quantum mechanics. In the quantum world, objects don't exist in definite states until they are observed. Instead, they are in a fluid, probabilistic state of all possibilities, only becoming real when we look at them. This raises deep philosophical questions about the nature of reality. Is reality something that exists independently of observation, or does the act of observation itself create reality? These are questions that physicists and philosophers alike have grappled with since the early days of quantum theory. Interestingly, this idea of superposition and wave function collapse has practical applications in one of the most exciting fields of modern science, quantum computing. Unlike classical computers, which use bits to represent either a 0 or a 1, quantum computers use quantum bits, or qubits, which can exist in superposition, representing both 0 and 1 simultaneously. This allows quantum computers to perform multiple calculations at once, potentially solving complex problems much faster than classical computers. In this way, quantum superposition is not just a theoretical curiosity, it's a powerful tool that could revolutionize computing, cryptography, and even artificial intelligence. As we continue our journey into the world of quantum physics, we will encounter even more strange and mind-bending phenomena. The uncertainty principle, a universe built on probability. In the quantum realm, certainty is an illusion. Unlike the macroscopic world, where the positions and speeds of objects can be predicted with great precision, the quantum world operates under a veil of uncertainty. One of the most famous and fundamental principles in quantum mechanics, the Heisenberg uncertainty principle, tells us that it is impossible to know both the exact position and exact momentum of a particle at the same time. This inherent fuzziness isn't due to limitations in our measurement tools. It's a fundamental feature of reality itself. Let's take a step back and consider how this idea first emerged. In 1927, German physicist Werner Heisenberg was grappling with the strange implications of quantum theory. As he delved deeper into the behavior of quantum particles like electrons, he realized something profound. The more precisely you try to measure one property of a particle, such as its position, the less precisely you can know another property, like its momentum. This trade-off isn't a result of experimental error, it's a fundamental property of the universe. To understand why this happens, let's consider a simple analogy. Imagine you're trying to observe a small object, like a pebble, on the surface of a pond. To see it more clearly, you shine a beam of light on it. In the classical world, this wouldn't be a problem. The light helps you observe the pebble, and you can determine both its position and how fast it's moving without any issues. But in the quantum world, particles like electrons are so small that the very act of shining light on them disturbs them. When you shine a photon of light on an electron to measure its position, that photon transfers energy to the electron, changing its momentum. So, the more accurately you measure the electron's position, the more you disturb its momentum. On the flip side, if you try to measure its momentum precisely, you'll have to use a lower energy photon, which makes it harder to pinpoint the electron's exact position. This is the essence of Heisenberg's uncertainty principle. There is a fundamental limit to how much we can know about a quantum system. The uncertainty principle is typically expressed in terms of an equation. The product of the uncertainty in position and the uncertainty in momentum must be greater than or equal to a constant known as Planck's constant, divided by 4 pi. In spoken terms, this means that as the uncertainty in one property decreases, the uncertainty in the other increases, and vice versa. This relationship is not just a technical limitation, it is built into the fabric of the quantum world. Now, you might be wondering, why is this important? What does this uncertainty mean for our understanding of reality? One of the most significant implications of the uncertainty principle is that it forces us to abandon the idea of determinism, the idea that the future can be predicted with absolute certainty if we know the present conditions precisely. In classical physics, the state of a system at any given time can, in principle, be calculated exactly if we know the initial conditions. Think of Isaac Newton's laws of motion, where the position and velocity of an object can be predicted with great precision. But in the quantum world, determinism breaks down. Because we can never know both the position and momentum of a particle with complete precision, we can never predict its future behavior with absolute certainty. Instead, we are left with probabilities. The best we can do is calculate the likelihood of a particle being in a particular position or having a particular momentum at a given time. This probabilistic nature of quantum mechanics is encapsulated in the wave function, which describes the probability distribution of a particle's position and momentum. This shift from determinism to probability marks a profound departure from classical physics. It suggests that at its most fundamental level, the universe is not a predictable clockwork mechanism, but rather a realm of possibilities. Particles do not have definite positions or velocities until they are observed. Instead, they exist in a cloud of probabilities, with different outcomes, more or less likely depending on the circumstances. Let's consider a famous thought experiment to illustrate this point: the quantum particle in a box. Imagine an electron confined to a small, one-dimensional box. According to classical physics, the electron should behave like a tiny billiard ball, bouncing back and forth inside the box, with a definite position and velocity at all times. But in the quantum world, the electron doesn't have a definite position. Instead, its wave function describes the probability of finding the electron at different positions within the box. The electron is smeared out across the box, and we can only calculate the probability of finding it in any given region. When we observe the electron, its wave function collapses, and we find the electron in a particular position. But before the observation, the electron's position was not well defined. It was spread out across the entire box, existing in a superposition of all possible positions. This is the probabilistic nature of the quantum world in action. The uncertainty principle also has profound implications for the nature of energy and time. Just as there is an uncertainty in position and momentum, there is also an uncertainty in energy and time. This means that for very short periods of time, a quantum system can borrow energy from the universe as long as it pays it back quickly enough. This idea is at the heart of a phenomenon known as quantum fluctuations, where particles can spontaneously pop in and out of existence in empty space. These quantum fluctuations are not just theoretical curiosities, they have real-world consequences. One of the most important examples of this is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a small but measurable force pulling them together. This force arises from quantum fluctuations in the vacuum between the plates, demonstrating that even empty space is teeming with activity at the quantum level. The uncertainty in energy and time also plays a crucial role in the process of quantum tunneling, where particles can pass through barriers that they would not be able to cross in classical physics. In classical physics, if a ball rolls toward a hill that is too high for it to climb, it will simply roll back down. But in the quantum world, particles like electrons can sometimes tunnel through energy barriers, even if they don't have enough energy to cross the barrier in the classical sense. This is because, for very short periods of time, the particle can borrow enough energy to tunnel through the barrier, as long as it pays back that energy quickly enough. Quantum tunneling is not just a theoretical phenomenon. It is essential to many processes in the universe, including nuclear fusion in stars. In fact, without quantum tunneling, the Sun would not be able to produce energy through fusion, and life on Earth would not exist. At the heart of the Sun, protons must overcome the repulsive force between their positive charges in order to fuse together and release energy. Classically, the temperature and pressure in the Sun's core would not be high enough for fusion to occur. But thanks to quantum tunneling, protons can tunnel through the energy barrier and fuse, powering the Sun's nuclear furnace. Quantum tunneling is also crucial to the operation of modern technologies, such as the semiconductor devices that power our computers and smartphones. In these devices, electrons tunnel through thin barriers between materials, allowing for the flow of electric current in ways that would not be possible in a purely classical system. The uncertainty principle, quantum tunneling, and the probabilistic nature of quantum mechanics all point to a universe that is far stranger and more unpredictable than we could have ever imagined. The classical picture of a deterministic clockwork universe has been replaced by a quantum reality where uncertainty and probability reign supreme. And yet, despite this uncertainty, the quantum world is not chaotic. It follows precise mathematical rules that govern the behavior of particles on the smallest scales and give rise to the rich and complex structures we see in the universe. As we continue to explore the quantum realm, we find that the uncertainty at the heart of quantum mechanics is not a limitation, but rather a window into the deeper hidden layers of reality. The universe, it seems, is not a fixed and predictable entity, but a dynamic and ever-changing tapestry of possibilities. In the next chapter, we will explore how quantum mechanics and general relativity, two of the most successful theories in physics, come into conflict when we try to describe the universe on both the largest and smallest scales. We will dive into the quest for a theory of quantum gravity and the tantalizing possibility that space and time themselves may emerge from quantum phenomena. The clash of titans, quantum mechanics versus general relativity. As we continue our journey through the quantum world, we arrive at one of the most profound challenges in modern physics: the conflict between quantum mechanics and Albert Einstein's theory of general relativity. Both of these theories are incredibly successful in their own right. Quantum mechanics describes the behavior of particles on the smallest scales. Atoms, electrons, photons, and even smaller particles like quarks. General relativity, on the other hand, describes the behavior of massive objects, from planets and stars to galaxies and black holes, as well as the very fabric of space and time. Each theory has been rigorously tested and validated by experiments and observations. And yet, when we try to combine them, things fall apart. At first glance, you might wonder why quantum mechanics and general relativity need to be combined at all. After all, they seem to describe completely different domains of the universe. Quantum mechanics deals with the microscopic realm, while general relativity deals with the macroscopic. But the universe doesn't have two sets of rules, one for the small and one for the large. Eventually, these two realms must overlap, especially when we consider objects like black holes, where gravity becomes incredibly strong and the quantum nature of particles becomes significant. One of the major areas where quantum mechanics and general relativity collide is in the description of black holes. Black holes are regions of space where gravity is so intense that not even light can escape. According to general relativity, black holes warp space and time to an extreme degree. Anything that crosses the event horizon, the boundary around the black hole, is pulled inward, eventually collapsing to a singularity, a point of infinite density and zero volume. At the singularity, general relativity breaks down, predicting infinities that don't make physical sense. This is where quantum mechanics enters the picture. Quantum theory tells us that particles cannot be confined to infinitely small points. Instead, they exist as probability clouds, spread out over space. When we try to apply quantum mechanics to the singularity of a black hole, the math breaks down, leading to contradictions and unresolved infinities. It becomes clear that general relativity, while incredibly successful at describing large-scale phenomena, cannot be the full story when it comes to extreme conditions like those inside a black hole. This leads us to one of the greatest unsolved problems in physics. How do we reconcile quantum mechanics and general relativity into a single, unified theory? Such a theory is often referred to as quantum gravity, and it would provide a complete description of the universe at all scales, from the tiniest particles to the largest cosmic structures. A theory of quantum gravity would not only describe black holes, but also the earliest moments of the universe, where both quantum effects and gravitational effects were incredibly strong. Let's take a moment to understand why this unification is so difficult. At its core, general relativity is a classical theory, meaning it deals with continuous quantities like smooth curves and well-defined positions. Space and time are treated as a continuous fabric, bending and warping in response to the presence of mass and energy. Quantum mechanics, on the other hand, deals with discrete quantities, like the energy levels of an electron in an atom, and with probabilities rather than certainties. In quantum mechanics, particles do not have definite positions or velocities until they are measured. Instead, they exist in superpositions of different states. One way to visualize the conflict between these two theories is to imagine a smooth rubber sheet, which represents the fabric of space-time according to general relativity. Now, imagine that instead of a smooth sheet, the fabric is made up of tiny discrete particles, more like a mesh or grid. This is how quantum mechanics views space on very small scales. When we try to describe space and time as both a continuous fabric and a discrete quantum structure, contradictions arise. One of the most promising approaches to resolving these contradictions is a theory called string theory. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings can vibrate in different ways, giving rise to different particles, such as electrons, quarks, or photons. In this framework, gravity emerges naturally from the vibrations of a particular type of string. This means that string theory provides a potential way to unite quantum mechanics and general relativity into a single framework. However, string theory is not without its challenges. One of the most significant issues is that it requires the existence of extra dimensions, not just the 3 dimensions of space and 1 of time that we experience, but additional dimensions that are hidden from view. In most versions of string theory, there are a total of 10 or 11 dimensions. These extra dimensions are thought to be compactified or curled up so tightly that we don't notice them in our everyday lives. While this may sound far-fetched, the mathematics of string theory suggests that these extra dimensions are necessary for the theory to be consistent. String theory has made significant progress in describing the fundamental forces of nature, but it is still a work in progress. It has yet to make concrete predictions that can be tested by experiments, and many physicists remain skeptical of its ability to fully describe quantum gravity. However, it remains one of the leading candidates for a unified theory of the universe. Another approach to quantum gravity is known as loop quantum gravity. Unlike string theory, which focuses on tiny vibrating strings, loop quantum gravity attempts to directly quantize space and time. In this theory, space and time are not continuous. Instead, they are made up of tiny, discrete loops. These loops form a network, like a microscopic web, and this network gives rise to the geometry of space-time. In loop quantum gravity, the smooth fabric of space-time that we experience at large scales is an emergent property of these tiny loops. This theory suggests that space and time themselves are quantized, much like energy levels in an atom. While both string theory and loop quantum gravity offer promising avenues for uniting quantum mechanics and general relativity, neither has yet provided a complete solution. The search for quantum gravity remains one of the greatest challenges in theoretical physics, and solving it would revolutionize our understanding of the universe. Nowhere is the conflict between quantum mechanics and general relativity more evident than in the study of black holes. In 1974, physicist Stephen Hawking made a groundbreaking discovery that brought these two theories into direct conflict. Hawking showed that black holes are not completely black. They can emit radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, where pairs of virtual particles pop in and out of existence due to quantum fluctuations. Sometimes one of these particles falls into the black hole, while the other escapes, effectively reducing the mass of the black hole over time. Hawking radiation poses a major puzzle for physicists because it suggests that black holes can eventually evaporate completely. But if a black hole evaporates, what happens to the information about the matter that fell into it? According to quantum mechanics, information cannot be destroyed, but in general relativity, the singularity at the center of a black hole seems to imply that information is lost forever. This paradox, known as the black hole information paradox, is one of the key issues that quantum gravity must resolve. The quest to unite quantum mechanics and general relativity is not just about solving technical problems. It's about understanding the deepest, most fundamental aspects of reality. What is the true nature of space and time? How do particles and forces emerge from the quantum fabric of the universe? These are questions that take us to the very limits of human knowledge and beyond. The multiverse, quantum worlds, and parallel realities. In our quest to unravel the mysteries of quantum mechanics, we now venture into one of the most mind-bending ideas in modern physics, the multiverse. Could it be that our universe, vast as it is just one of an infinite number of universes? Could there be countless parallel worlds, each with different physical laws, constants, and even different versions of ourselves. The concept of the multiverse stretches our imagination to its limits and challenges everything we think we know about reality. The idea of a multiverse didn't emerge from science fiction. It is rooted in quantum mechanics and cosmology. The possibility of multiple universes arises from the peculiar and deeply puzzling features of quantum theory, such as wave function collapse and quantum superposition, as well as the strange nature of cosmic inflation in the early moments of the universe. Let's start with quantum mechanics and the famous many worlds interpretation. As we discussed in earlier chapters, quantum mechanics tells us that particles exist in superpositions of multiple states until they are observed. When we measure a quantum system, the wave function, the mathematical description of all possible outcomes, collapses into a single definite state. But what if the wave function doesn't actually collapse? What if, instead, all possible outcomes happen simultaneously, each in its own separate universe? This is the central idea behind the many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett in 1957. According to this interpretation, every time a quantum event occurs, every time a particle is observed or measured, the universe splits into multiple branches, one for each possible outcome. In one branch, the particle takes on one value, and in another branch, it takes on a different value. These branches represent parallel universes, each as real as the one we inhabit, but forever separated from one another. In the many worlds interpretation, every possible outcome of every quantum event exists in its own universe. Imagine you are flipping a quantum coin. In one universe, the coin lands heads, and in another, it lands tails. Both universes exist, but we are only aware of the one in which we observe the outcome. In this way, the many worlds interpretation suggests that the entire universe is constantly splitting into countless parallel realities. This idea may sound far-fetched, but it is one of the most elegant solutions to the problem of wave function collapse in quantum mechanics. Rather than assuming that only one outcome is real and the others simply vanish, the many worlds interpretation allows all outcomes to exist, just in different universes. In this view, there is no need for wave function collapse at all. The universe simply branches into multiple realities every time a quantum event occurs. The implications of this are staggering. If the many worlds interpretation is correct, then there are countless versions of you existing in parallel universes, each living out different possible outcomes of your choices and actions. In one universe, you might have taken a different job. In another, you might have chosen a different path in life entirely. Every decision, every quantum event creates a new branch of the multiverse, leading to an infinite number of parallel realities. But the multiverse idea doesn't stop with quantum mechanics. It also arises from cosmology, particularly from the theory of cosmic inflation. In the 1980s, physicist Alan Guth proposed the idea of inflation, a period of extremely rapid expansion that occurred in the very early moments of the universe. This inflationary phase explains why the universe appears so flat and uniform on large scales, and it has been supported by a wide range of observations, including the cosmic microwave background radiation. However, inflation has some strange implications. According to some versions of inflation theory, the rapid expansion of space didn't stop uniformly everywhere. In some regions, inflation may have continued, causing these regions to expand into their own separate universes. This leads to the concept of eternal inflation, where inflation never fully ends, but instead creates a vast, ever-expanding multiverse with countless pocket universes forming in different regions of space-time. Each of these pocket universes could have its own set of physical laws and constants. In some universes, gravity might be stronger. In others, the speed of light might be different. Some universes might support the formation of stars and planets, while others might be completely lifeless. Our universe, with its particular set of physical constants that allow for the formation of life, is just one of these countless possibilities. The multiverse idea also finds support in string theory, which, as we explored in the previous chapter, suggests that the fundamental building blocks of the universe are tiny vibrating strings. String theory predicts the existence of extra dimensions beyond the 3 dimensions of space and one of time that we experience. These extra dimensions could be compactified or hidden, but they also open the door to the possibility of parallel universes. In some versions of string theory, different branes, multidimensional objects, can exist in a higher dimensional space, each representing a different universe. If these branes exist, our universe could be just one brane among many, floating in a higher dimensional space. Other branes could represent entirely separate universes, with their own physical laws and constants. Occasionally, these branes could even collide, leading to dramatic events like the Big Bang, which might have been the result of such a collision in our universe's distant past. The idea of a multiverse, whether arising from quantum mechanics, inflationary cosmology, or string theory, raises profound questions about the nature of reality. Is our universe just one of many? Are there other versions of ourselves living out different lives in parallel realities? And if there are multiple universes, could we ever detect them or travel between them? One of the most exciting possibilities for detecting other universes comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. Some physicists believe that if our universe collided with another universe in the past, it might have left an imprint on the cosmic microwave background in the form of unusual patterns or temperature fluctuations. While no definitive evidence of such collisions has been found, future observations with more precise instruments could provide clues. Another potential way to detect parallel universes comes from black holes. Some theories suggest that black holes could act as gateways to other universes. When matter falls into a black hole, it is compressed to an incredibly small point at the singularity. But instead of being destroyed, this matter could be ejected into another universe, creating a new Big Bang in that universe. This idea, known as black hole cosmology, suggests that each black hole in our universe could be the seed of a new universe, existing independently from our own. The multiverse also raises deep philosophical questions about the nature of existence. If there are infinite universes, each with different versions of you, what does that say about your identity? Are you just one of countless copies, or is there something unique about the version of you that exists in this universe? And if every possible outcome of every event happens in some universe, does that mean that free will is an illusion, with every decision you make playing out in parallel worlds? These questions push the boundaries of what we can understand about the universe and our place within it. While the multiverse remains a highly speculative idea, it is a natural consequence of some of the most successful theories in physics. Whether or not we ever find direct evidence of other universes, the concept forces us to rethink our understanding of reality on a cosmic scale. In the next chapter, we will explore how quantum mechanics and the multiverse connect to the mysteries of time itself. Is time an illusion, or does it have a fundamental existence? Can we travel through time? And if so, what role does quantum mechanics play in shaping the flow of time? Get ready to dive into the enigma of time and how it fits into the quantum world. Time in the quantum realm. Is time an illusion? Time. It is one of the most fundamental aspects of our experience of reality, and yet, when we delve into the world of quantum mechanics, time becomes one of the greatest mysteries. What is time? Does it flow like a river, constantly moving forward? Or is it an illusion, a construct that we impose on a more fundamental, timeless reality? In our everyday lives, time seems simple enough. We experience the present moment, remember the past, and anticipate the future. Time marches on, second by second, minute by minute, always moving forward. This notion of time as a linear progression from the past through the present to the future is deeply ingrained in our understanding of the world. However, when we start to explore the quantum realm, this simple picture of time begins to break down. In classical physics, time is treated as a continuous universal parameter, a backdrop against which events unfold. Isaac Newton viewed time as absolute, flowing at a constant rate, independent of the objects or events that occur within it. But in both quantum mechanics and Einstein's theory of relativity, time takes on a much stranger and more fluid character. Let's start by considering how time is treated in relativity. In Einstein's theory of general relativity, time is not an absolute universal parameter. Instead, time is intertwined with space, forming a four-dimensional fabric called space-time. Massive objects like planets and stars warp the fabric of space-time, causing both space and time to curve. This means that time does not flow at the same rate everywhere in the universe. In fact, the stronger the gravitational field, the slower time flows. This effect, known as time dilation, has been experimentally confirmed using precise clocks placed at different altitudes on Earth. A clock at sea level, where gravity is stronger, ticks more slowly than a clock on a mountain, where gravity is weaker. Relativity also tells us that time is relative. It depends on the observer's frame of reference. For example, if you were to travel near the speed of light, time for you would slow down, relative to someone who is standing still. This is known as time dilation due to velocity. In extreme cases, such as near a black hole, time can slow down so much that it effectively stops. This means that if you were to fall into a black hole, someone observing from a distance would see your motion slow down to a halt as you approach the event horizon. From your perspective, however, time would continue to flow normally. But what about time in the quantum world? In quantum mechanics, time is treated somewhat differently. Quantum systems evolve over time according to the Schrödinger equation, which describes how a quantum system's wave function changes. The key difference here is that while general relativity treats time as a dynamic, relative quantity, quantum mechanics treats it as a fixed parameter. Time in quantum mechanics is absolute and external. It is not affected by the quantum system itself. This creates a fundamental tension between quantum mechanics and general relativity, where time is part of the dynamical fabric of the universe. This tension between the treatment of time in quantum mechanics and relativity has profound implications for our understanding of the universe. If we hope to develop a unified theory that combines quantum mechanics with general relativity, we will need a new understanding of time that works at both the quantum and cosmic scales. This is one of the key challenges in the quest for a theory of quantum gravity, as we explored in earlier chapters. One of the most intriguing ideas that has emerged from this tension is the possibility that time itself may not be fundamental. Some physicists believe that time, rather than being a basic feature of the universe, might be an emergent property, something that arises from more fundamental processes. In this view, time is not an independent entity, but instead emerges from the interactions of quantum particles or fields. Just as temperature is an emergent property of the collective motion of molecules, time might be an emergent property of the underlying quantum reality. But if time is emergent, what does that mean for our experience of the present, past, and future? One possibility is that the flow of time, the sensation that time moves forward, is an illusion created by our perception of change. In the quantum world, particles exist in a superposition of states, meaning they can be in multiple places or have multiple properties at once. It is only when we observe the system that it collapses into a definite state, giving the appearance of change over time. Some physicists argue that this collapse gives rise to the illusion of time's passage, even though, at the quantum level, all states of the system exist simultaneously. This idea is closely related to the block universe theory, which comes from the relativistic view of space-time. In the block universe, time is not something that flows, but is instead like a spatial dimension. The past, present, and future all exist equally, just as all points in space exist equally. In this view, the present moment is no more special than any other moment in time, and our perception of time flowing from past to future is simply a feature of how we experience the universe. The block universe raises fascinating questions about the nature of free will. If the future already exists, just as the past does, then are we truly free to make choices, or are our actions predetermined by the structure of space-time? While this is a philosophical question as much as a scientific one, it underscores the deep connections between quantum mechanics, time, and the nature of reality. Quantum mechanics also gives rise to another strange feature of time reversibility. In classical physics, most processes are time reversible, meaning that if you ran the process backward, it would look just as valid as running it forward. For example, if you watch a video of a ball rolling on a flat surface, you wouldn't be able to tell whether the video was being played forward or in reverse. But in the real world, many processes are irreversible. Think of an ice cube melting in a glass of water. Once the ice has melted, it cannot spontaneously reform into an ice cube, and the water cannot return to its original state without adding energy. This irreversibility is a key feature of thermodynamics governed by the second law, which states that the entropy, or disorder, of a system tends to increase over time. In quantum mechanics, however, time reversal symmetry plays an important role. The Schrödinger equation that governs the evolution of quantum systems is time reversible, meaning that if you were to reverse time, the quantum system would evolve in a way that is mathematically valid. This leads to the puzzling question of why time seems to flow in one direction for large-scale systems, but can be reversed at the quantum level. One possible explanation lies in the concept of quantum decoherence, where the interactions of a quantum system with its environment cause the system to lose its quantum coherence, effectively locking it into a particular outcome and creating the appearance of time flowing in one direction. The interplay between quantum mechanics and thermodynamics brings us to another fascinating question: the nature of the arrow of time. Why does time seem to flow in one direction from the past to the future rather than being symmetric? The most commonly accepted explanation is that the arrow of time is tied to the increase of entropy in the universe. The universe started in a state of low entropy, a highly ordered state, and as it evolves, entropy increases, leading to a more disordered state. This increase in entropy gives rise to the forward flow of time. But what caused the universe to start in such a low entropy state in the first place? This is one of the great unsolved mysteries in cosmology. The study of time in quantum mechanics also opens up the tantalizing possibility of time travel. If time is not a fundamental property of the universe, but rather an emergent phenomenon, then perhaps it could be manipulated or altered. Some theories, including certain interpretations of general relativity, suggest that time travel might be possible through structures known as closed time-like curves. These are paths in space-time that loop back on themselves, allowing an object to return to its own past. While time travel remains speculative and faces numerous paradoxes, such as the famous grandfather paradox, where a time traveler could theoretically prevent their own existence by altering the past. The idea has captivated both scientists and science fiction writers alike. In the quantum world, some researchers have even explored the possibility of quantum time travel, where quantum systems could be sent backward in time in ways that avoid the paradoxes of classical time travel. As we continue to explore the mysteries of time in the quantum realm, we are forced to confront some of the deepest questions about the nature of reality. Is time an illusion? Can it be reversed or manipulated? And how does our perception of time relate to the underlying quantum processes that govern the universe? In the next chapter, we will delve into one of the most mind-bending consequences of quantum mechanics, the idea that consciousness itself may play a role in shaping reality. Could the act of observation bring the universe into existence? We'll explore the controversial topic of the observer effect and its implications for our understanding of the cosmos. The observer effect. Does consciousness shape reality? Quantum mechanics has taken us on a wild journey through the smallest scales of the universe, revealing phenomena that seem to defy our everyday experiences. But one of the most perplexing aspects of quantum theory is the role of the observer in shaping reality. This idea, often referred to as the observer effect, suggests that the very act of observing a quantum system can affect its outcome. Could it be that consciousness itself plays a fundamental role in the workings of the universe? Does reality only exist because we are here to observe it? To understand the observer effect, we need to return to one of the most famous experiments in quantum mechanics, the double-slit experiment. In this experiment, a beam of light or particles, such as electrons, is fired at a screen with two narrow slits. On the other side of the slits is a detector screen that records where the particles land. When both slits are open, but no one is observing which slit the particles pass through, they behave like waves, creating an interference pattern on the detector screen, a pattern of light and dark bands that results from the wave-like nature of the particles interfering with themselves. However, when an observer places a detector to measure which slit the particle passes through, the interference pattern disappears, and the particles behave like classical particles, passing through one slit or the other, and landing in two distinct regions on the detector screen. In other words, the mere act of observing the particles changes their behavior from waves to particles. This puzzling result has led many to wonder about the nature of observation itself. How can the simple act of measuring or observing a quantum system affect its outcome? Is the universe fundamentally different when we are not looking? This is where the observer effect comes into play, and it raises deep philosophical questions about the nature of reality and consciousness. At the heart of the observer effect is the concept of wave function collapse. In quantum mechanics, particles are described by wave functions, which encode all the possible outcomes of a measurement. Before a measurement is made, the particle exists in a superposition of all possible states. It can be in multiple places, have multiple energies, or possess multiple spins simultaneously. But when we observe or measure the system, the wave function collapses, and the particle chooses a definite state. The key question is, what causes the wave function to collapse? In the traditional interpretation of quantum mechanics, known as the Copenhagen interpretation, observation or measurement is what causes the collapse. This has led some to speculate that consciousness, the awareness of the observer, plays a role in shaping reality. After all, it seems that reality only solidifies when we observe it. One of the most famous proponents of this idea was physicist John Archibald Wheeler, who proposed the concept of the participatory universe. According to Wheeler, the universe is not a pre-existing entity that simply unfolds according to deterministic laws. Instead, reality is shaped by the observations and interactions of conscious beings. Wheeler famously suggested that no phenomenon is a real phenomenon until it is an observed phenomenon. In this view, the universe exists in a state of potentiality, and it is through observation and measurement that reality takes on its definitive form. This idea brings us to one of the most debated interpretations of quantum mechanics: the role of consciousness in the collapse of the wave function. Could it be that our conscious minds are not just passive observers of the universe, but active participants in shaping reality? Some interpretations of quantum theory, such as the von Neumann-Wigner interpretation, suggest that consciousness may be the key to understanding wave function collapse. In this view, the conscious observer plays a direct role in determining the outcome of quantum events. However, this interpretation is highly controversial and remains a minority view among physicists. Most physicists prefer interpretations that do not invoke consciousness as a fundamental element of quantum mechanics. After all, the idea that consciousness plays a role in the collapse of the wave function raises many difficult questions. For one, how do we define consciousness in the context of quantum mechanics? Is it simply the presence of an observer, or does it require self-awareness and subjective experience? Moreover, if consciousness collapses the wave function, then what about inanimate measuring devices? Quantum experiments often use detectors, such as photodetectors or Geiger counters, to measure the properties of particles. These devices are not conscious, yet they seem to cause wave function collapse just as effectively as a human observer. This suggests that it is not consciousness itself that collapses the wave function, but the interaction between the quantum system and a classical measuring device. To resolve this issue, some physicists propose that measurement is what causes the wave function to collapse, but measurement doesn't require consciousness. In this view, any interaction between a quantum system and a macroscopic classical object is enough to cause collapse. For example, when a photon strikes a photodetector, it interacts with the macroscopic device, transferring its quantum information to the classical world, and the wave function collapses. Consciousness is not necessary for this process. This idea is further supported by the theory of quantum decoherence, which provides a possible explanation for how classical outcomes emerge from quantum superpositions. Decoherence occurs when a quantum system interacts with its environment, causing the system to lose its quantum coherence, the delicate superposition of states. As a result, the system appears to behave classically with definite outcomes. Decoherence explains why we do not observe quantum superpositions in our everyday world, even though they are fundamental to the quantum realm. It suggests that the apparent collapse of the wave function is the result of interactions between the quantum system and its environment, not the presence of a conscious observer. While decoherence offers a compelling explanation for the transition from quantum to classical behavior, it still leaves open questions about the nature of observation. What, after all, is the difference between a conscious observer and a measuring device? And does the universe exist independently of our observations, or is reality only brought into being when we observe it? To explore these questions, we can turn to another famous quantum thought experiment, Schrödinger's cat. In this thought experiment, proposed by physicist Erwin Schrödinger in 1935, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation from the decaying atom, the hammer breaks the vial, releasing the poison and killing the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of decayed and undecayed states until it is measured. Therefore, the cat is also in a superposition of being both alive and dead until the box is opened and an observation is made. Schrödinger's cat is a paradox that illustrates the strange implications of quantum mechanics. The cat, in some sense, is both alive and dead until an observer checks its state. This raises the question: when does the superposition collapse into one definite outcome? Does the cat itself count as an observer, or is a conscious human required to open the box and determine the outcome? Schrödinger's cat forces us to confront the role of the observer in quantum mechanics. Does the universe exist in a definite state when we are not looking, or does it exist in a superposition of possibilities until an observation is made? Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that the cat is both alive and dead in different branches of the multiverse. In one universe, the cat survives, while in another, the cat perishes. In this view, observation does not collapse the wave function, but instead separates reality into multiple coexisting branches. Other interpretations, such as the Copenhagen interpretation, hold that observation collapses the wave function, creating a single definite outcome. In this case, opening the box collapses the superposition, and the cat is either alive or dead, but not both. The Copenhagen interpretation emphasizes the role of measurement in determining the outcome, but it remains agnostic about whether consciousness is required for this process. The role of the observer in quantum mechanics remains one of the most hotly debated topics in physics. While there is no consensus on whether consciousness plays a fundamental role in shaping reality, the observer effect has led to some profound philosophical implications. It forces us to reconsider the nature of reality and the relationship between the observer and the observed. Are we passive witnesses to an objective universe, or are we active participants shaping reality through our observations? As we ponder these questions, it is worth noting that the observer effect is not limited to the quantum realm. In fact, it has analogs in many other areas of science and philosophy. For example, in psychology, the observer effect refers to the phenomenon where people change their behavior when they know they are being observed. Similarly, in sociology, the Hawthorne effect describes how individuals modify their behavior in response to being studied. In these cases, observation influences outcomes in ways that mirror the observer effect in quantum mechanics. Ultimately, the observer effect challenges our assumptions about the nature of reality. It suggests that reality may not be fixed and objective, but instead depends on interactions between the observer and the observed. While quantum mechanics may offer only glimpses into this deep mystery, it opens the door to questions that transcend physics and touch on the very nature of existence itself. In the next chapter, we will dive into one of the most profound implications of quantum mechanics: the concept of quantum entanglement. Could particles be connected across vast distances, with changes in one particle instantly affecting the other, even faster than the speed of light? We'll explore the mind-bending phenomenon of entanglement and what it reveals about the interconnectedness of the universe. Quantum entanglement, spooky action at a distance. If there's one phenomenon in quantum mechanics that has truly captivated the imagination of scientists, philosophers, and the public alike, it's quantum entanglement. Albert Einstein famously called it spooky action at a distance, and for good reason. Entanglement challenges our classical notions of separability and locality, suggesting that particles can be deeply connected even when separated by vast distances. It's a phenomenon that seems to defy common sense, yet it has been experimentally confirmed time and time again. Entanglement is one of the most mysterious and counterintuitive aspects of quantum mechanics, and it raises profound questions about the nature of reality itself. In this chapter, we'll explore what entanglement is, how it works, and what it reveals about the underlying fabric of the universe. What is quantum entanglement? To understand quantum entanglement, let's begin with the basics. In quantum mechanics, particles such as electrons or photons can become entangled when they interact with one another in certain ways. Once two particles are entangled, their quantum states become linked, meaning that the state of one particle cannot be described independently of the state of the other, no matter how far apart they are. Imagine two particles, say electrons, that are created together in a specific quantum state. According to quantum mechanics, these particles don't have definite properties, like spin, until they are measured. Instead, they exist in a superposition of all possible states. But because the particles are entangled, if you measure the spin of one particle, the spin of the other particle is instantly determined, no matter how far away it is. If you measure the first particle to have upspin, the second particle will instantly have downspin, even if it's on the other side of the galaxy. This is where the spooky part comes in. How can information about the state of one particle be transmitted to the other faster than the speed of light? According to Einstein's theory of relativity, nothing can travel faster than light, so how can entanglement allow for instantaneous connections between distant particles? This apparent violation of the speed of light puzzled Einstein, who believed that there must be some hidden variables, unknown factors that determine the outcomes of quantum measurements in a way that preserves locality and causality. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a famous paper known as the EPR paradox. In this paper, they argued that quantum mechanics must be incomplete because it allows for these seemingly instantaneous, non-local connections between particles. They believed that there must be a more complete theory, one that would explain entanglement without violating the principle of locality. This more complete theory would include hidden variables that would determine the outcomes of measurements in a way that was consistent with classical physics. However, over the next few decades, quantum mechanics continued to defy these classical expectations. In the 1960s, physicist John Bell proposed an experiment that could test whether or not hidden variables were at play. Bell's theorem showed that if quantum mechanics were correct, certain statistical correlations between entangled particles would be stronger than what would be allowed by any hidden variable theory that respected locality. In other words, Bell's theorem provided a way to experimentally test whether quantum entanglement truly involved faster-than-light connections or whether it could be explained by hidden variables. The results of these experiments were astonishing. In the 1980s, physicist Alain Aspect and his team conducted a series of experiments that confirmed the predictions of quantum mechanics. The correlations between entangled particles were indeed stronger than what any local hidden variable theory could explain. This meant that Einstein's hope for a classical explanation was dashed and quantum entanglement was real. Particles could indeed influence each other instantly, no matter how far apart they were, without any hidden variables. How does entanglement work? At its core, quantum entanglement challenges our classical intuition about how the universe works. In classical physics, objects are separable. If you have two objects and separate them by a large distance, what happens to one object has no effect on the other. But in the quantum world, things are different. Entangled particles are not independent of each other, even when separated by vast distances. They are part of a single, inseparable quantum system. The key to understanding entanglement lies in the concept of superposition. Before being measured, quantum particles don't have definite properties. Instead, they exist in a superposition of all possible states. When two particles become entangled, their individual superpositions become linked, meaning that the measurement of one particle's state will instantaneously determine the state of the other, no matter how far apart they are. But here's the twist. No information is actually transmitted between the two particles. Quantum mechanics doesn't violate the speed of light because nothing is traveling faster than light. Instead, the entangled system behaves as a single, non-local entity where the outcomes of measurements on one part of the system are instantly correlated with the outcomes on the other part. This phenomenon doesn't involve any communication between the particles in the classical sense. It's simply how the quantum system behaves as a whole. To understand this better, let's use a metaphor. Imagine you have two dice that are quantum entangled. When you roll one dice, the outcome of the other dice is instantly determined, even if it's on the other side of the universe. Now, you might think that the dice must be communicating with each other in some way to ensure that their outcomes are correlated. But in the quantum world, this communication isn't necessary. The two dice are part of the same quantum system, and their outcomes are linked no matter the distance between them. The reality of quantum entanglement has profound implications for our understanding of the universe. First, it challenges the classical notion of separability. In classical physics, objects are thought to have well-defined properties, independent of any other objects. But in the quantum world, entangled particles do not have independent properties. Their properties are only defined in relation to each other. Second, quantum entanglement challenges the principle of locality, the idea that objects can only influence each other through direct physical interactions. In classical physics, if one object affects another, it must do so by sending a signal or force that travels between them. But in the case of entanglement, there is no need for such a signal. The two particles are connected in a way that transcends space and time, making them behave as a single system, even when separated by great distances. This leads us to another mind-bending question. What does quantum entanglement tell us about the nature of reality? If entangled particles are part of a single system, then perhaps the universe itself is more interconnected than we realize. Some physicists, such as David Bohm, have suggested that quantum entanglement points to a deeper underlying reality, a holistic universe in which everything is interconnected at a fundamental level. Bohm's interpretation of quantum mechanics, known as the implicate order, suggests that the apparent separateness of objects in the universe is an illusion. In reality, everything is connected in a deeper, hidden order, and what we perceive as separate particles and objects are merely projections of this underlying unity. In this view, quantum entanglement is a glimpse into this deeper level of reality, where space and time are not fundamental, and the universe is a seamless whole. Entanglement also has practical implications, particularly in the field of quantum computing and quantum cryptography. Quantum computers, which use quantum bits or qubits, rely on the phenomenon of superposition and entanglement to perform calculations much more efficiently than classical computers. Entangled qubits can be used to perform operations on multiple possible outcomes simultaneously, vastly increasing computational power. Quantum cryptography, on the other hand, uses entanglement to create secure communication channels. Because the properties of entangled particles are perfectly correlated, any attempt to eavesdrop on the communication would disturb the system, making the intrusion detectable. This makes quantum cryptography potentially unbreakable, as any interference would immediately be noticed. Quantum entanglement is not without its paradoxes. One of the most famous is the EPR paradox, proposed by Einstein, Podolsky, and Rosen. As we mentioned earlier, the EPR paradox was meant to show that quantum mechanics is incomplete, as it allows for instantaneous connections between distant particles. But while experiments have confirmed the reality of entanglement, the paradox remains. How can particles be connected across vast distances without violating the speed of light? Another mystery of entanglement is how it relates to the concept of quantum non-locality. In classical physics, the idea of locality means that objects can only interact through direct physical contact or through signals that travel at or below the speed of light. But entanglement seems to defy this principle. Entangled particles are non-local, meaning that their correlations cannot be explained by any signal or interaction that travels between them. This raises the question: does quantum mechanics violate locality, or is there some deeper explanation that we have yet to uncover? Some physicists have suggested that entanglement could be evidence of a hidden structure to space-time itself. If space and time are not fundamental but emergent properties of a deeper quantum reality, then entanglement might be a clue to understanding this deeper structure. In this view, space-time could be a kind of hologram projected from a more fundamental, non-local reality. Finally, quantum entanglement forces us to rethink our understanding of causality. In classical physics, events are causally related. A cause leads to an effect, and this relationship is governed by the flow of time. But in the quantum world, cause and effect seem to blur. In the case of entangled particles, there is no clear causal relationship between the measurement of one particle and the state of the other. The two particles are correlated, but there is no signal or force traveling between them to establish this correlation. This challenges our classical notion of causality, where events unfold in a linear, time-ordered fashion. One way to think about this is to consider that in the quantum world, time itself might not be as fundamental as we believe. Some physicists have suggested that time, like space, could be an emergent property of a deeper, timeless reality. In this scenario, quantum entanglement may hint at a universe where events are not bound by the usual constraints of time and space, but are instead interconnected in a more profound and subtle way. The implications of quantum entanglement extend far beyond our current understanding of the universe. It's possible that entanglement holds the key to some of the deepest questions in physics, including the nature of space, time, and information. In recent years, researchers have explored the possibility that quantum entanglement is not just a curious feature of the quantum world, but a fundamental aspect of the structure of space-time itself. This idea comes from the field of quantum gravity, which seeks to unify quantum mechanics with general relativity, the theory that describes the behavior of gravity and the large-scale structure of the universe. One of the leading approaches to quantum gravity is known as the holographic principle. According to this principle, the information contained within a volume of space can be described by the information encoded on the boundary of that space, much like a hologram, where a three-dimensional image is projected from a two-dimensional surface. In this view, space-time itself might emerge from more fundamental quantum processes, and quantum entanglement could be the key to understanding how this happens. Recent research has shown that the structure of space-time in certain theories of quantum gravity can be described in terms of quantum entanglement. In these theories, the fabric of space-time is woven together by the entanglement of quantum particles. This suggests that space and time are not fundamental entities, but are instead emergent properties of a deeper quantum reality. If this is true, then quantum entanglement could be the glue that holds the universe together, and understanding it could be the key to unlocking the mysteries of quantum gravity. The study of quantum entanglement has also led to new insights into the nature of black holes. In particular, researchers have explored the idea that the mysterious interiors of black holes, regions known as singularities where space-time breaks down, might be described by quantum entanglement. Some theories suggest that the information about everything that falls into a black hole is stored in the quantum entanglement of the particles that make up the black hole's event horizon. This idea, known as the holographic black hole, is part of a broader effort to understand the relationship between quantum mechanics, information, and gravity. In addition to its implications for fundamental physics, quantum entanglement has the potential to revolutionize technology. As we mentioned earlier, quantum computers harness the power of entanglement to perform calculations that would be impossible for classical computers. In the future, quantum computers could solve problems in fields like cryptography, material science, and artificial intelligence that are currently beyond our reach. Quantum entanglement is also at the heart of quantum teleportation, a process that allows information to be transferred instantly between two entangled particles. While this might sound like science fiction, quantum teleportation has already been demonstrated in laboratory experiments. Researchers have used entangled particles to transfer quantum information over distances of up to hundreds of kilometers. In the future, quantum teleportation could be used to develop ultra-secure communication networks that are immune to hacking. Quantum entanglement forces us to confront one of the most profound questions in science and philosophy. What is the nature of reality? In the classical view of the universe, reality is local and objective. Objects have definite properties, and these properties exist independently of whether or not we observe them. But quantum entanglement challenges this view, suggesting that reality is much stranger and more interconnected than we ever imagined. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that entanglement reveals the existence of parallel universes. In this view, every time a quantum measurement is made, the universe splits into multiple branches, each representing a different possible outcome. In one branch, the particle has up spin, and in another, it has down spin. All of these branches coexist in a vast multiverse, where every possible outcome of every quantum event plays out in a different universe. Other interpretations, such as the Copenhagen interpretation, suggest that entanglement reveals a fundamental indeterminacy in the universe. According to this view, the properties of quantum particles are not determined until they are measured. Before measurement, particles exist in a superposition of all possible states, and it is only the act of measurement that brings one particular outcome into reality. Whatever the true nature of entanglement may be, it challenges our classical intuitions and forces us to rethink the fundamental concepts of space, time, and information. It suggests that the universe is far more interconnected than we ever realized, and that the boundaries between objects, events, and observers may be more fluid and permeable than we once thought. Quantum entanglement is one of the most fascinating and mysterious phenomena in physics. It defies our classical understanding of the universe, suggesting that particles can be connected across vast distances, with changes in one particle instantly affecting the other. It challenges our notions of separability, locality, and causality, and it has profound implications for our understanding of space, time, and information. Through experiments like Bell's theorem, we have confirmed that entanglement is a real and fundamental feature of the quantum world. Yet, despite our growing understanding of how entanglement works, it remains one of the great mysteries of quantum mechanics. Does it reveal a deeper, non-local reality, or is it simply a consequence of the strange mathematics of the quantum world? Whatever the answer may be, entanglement has opened up new frontiers in both fundamental physics and technology. From quantum computing to quantum cryptography to quantum teleportation, entanglement holds the promise of revolutionizing the way we understand and interact with the universe. In the next chapter, we will explore the intersection of quantum mechanics and biology. Could the strange phenomena of the quantum world play a role in the processes of life itself? We'll dive into the emerging field of quantum biology and explore the possibility that life harnesses quantum mechanics in ways we are only beginning to understand. Quantum biology. Does life exploit quantum mechanics? Quantum mechanics is often thought of as the domain of tiny particles, operating far below the scales of everyday life. But what if quantum mechanics plays a more significant role in the natural world than we ever imagined? Could the strange and counterintuitive phenomena of the quantum world, such as superposition, entanglement, and tunneling, be at work within living organisms? This is the bold question posed by the emerging field of quantum biology, which seeks to understand whether life itself harnesses the laws of quantum mechanics to function in ways we are only beginning to understand. In this chapter, we will explore the intersection of quantum mechanics and biology, diving into the most intriguing examples of quantum processes potentially influencing the behavior of living organisms. From photosynthesis to bird navigation and even the processes of consciousness, quantum biology offers a tantalizing glimpse into the hidden quantum mechanisms that might underlie life itself. Photosynthesis is one of the most fundamental processes for life on Earth. It is how plants, algae, and certain bacteria convert sunlight into chemical energy, which is then used to fuel their growth and metabolism. But recent discoveries have suggested that the process of photosynthesis might not be purely a classical biochemical phenomenon. Instead, it could be influenced by quantum mechanics. The key to this quantum phenomenon lies in the first step of photosynthesis, the transfer of energy from sunlight to the reaction centers in the plant's chloroplasts. When light strikes a pigment molecule in the plant, such as chlorophyll, it excites an electron, boosting it to a higher energy state. This energy is then transferred through a series of molecules to the reaction center, where it is used to power the production of energy-rich molecules like ATP and glucose. But here's where quantum mechanics comes in. The energy transfer in photosynthesis is incredibly efficient, nearly 100%. Classical models of energy transfer, which rely on random hopping between molecules, cannot explain this level of efficiency. Instead, researchers have proposed that the energy is transferred through quantum coherence, a process in which the energy exists in a superposition of multiple states, allowing it to sample all possible pathways simultaneously and choose the most efficient route to the reaction center. This quantum superposition allows the energy to travel through the plant's molecular network like a wave, exploring multiple paths at once and quickly finding the most efficient route. Once the most efficient path is identified, the energy collapses into a single state and follows that path to the reaction center. This process, known as quantum coherence, has been experimentally observed in photosynthetic systems, suggesting that quantum mechanics plays a key role in the efficiency of photosynthesis. The discovery of quantum coherence in photosynthesis has profound implications for both biology and technology. It suggests that nature may have evolved to exploit quantum mechanics in ways that enhance the efficiency of biological processes. Moreover, understanding how quantum mechanics contributes to photosynthesis could lead to new technologies that mimic nature's quantum efficiency, such as ultra-efficient solar panels or quantum-inspired energy transfer systems. Enzymes are biological molecules that catalyze chemical reactions in living organisms, making them proceed faster than they would on their own. Enzymes are responsible for everything from digesting food to synthesizing DNA, and without them, the chemical reactions that sustain life would occur far too slowly to be useful. But how do enzymes work so efficiently? Classical models of enzyme function suggest that they lower the activation energy required for a chemical reaction to occur, allowing the reaction to proceed more quickly. However, recent research has shown that quantum mechanics might play a role in enzyme catalysis, particularly through a phenomenon known as quantum tunneling. Quantum tunneling occurs when particles pass through energy barriers that would be insurmountable in classical physics. In classical terms, a particle must have enough energy to overcome a barrier to reach the other side. But in the quantum world, particles can tunnel through barriers, even if they don't have enough energy to climb over them. This quantum tunneling effect has been observed in enzyme-catalyzed reactions, where protons and electrons can tunnel through energy barriers that would normally slow down or prevent the reaction. By allowing particles to tunnel through these barriers, enzymes can speed up chemical reactions beyond what classical chemistry would predict. This suggests that enzymes have evolved to take advantage of quantum mechanics to enhance their catalytic efficiency. Quantum tunneling in enzymes is an example of how life might use quantum mechanics to perform tasks that would be difficult or impossible under classical laws. It also raises the intriguing possibility that quantum mechanics could be a fundamental aspect of many biological processes, allowing life to operate with incredible efficiency at the molecular level. One of the most mysterious and fascinating examples of quantum biology comes from the world of animal behavior. Birds, particularly migratory species, have an astonishing ability to navigate over long distances, often traveling thousands of miles to reach their destinations. While some aspects of bird navigation are understood, such as the use of visual landmarks, the sun, and stars, one of the biggest mysteries has been how birds sense the Earth's magnetic field, which they use to orient themselves during migration. This magnetic sense, or magnetoreception, has long puzzled scientists. Birds seem to be able to detect the Earth's magnetic field with extraordinary sensitivity, but the exact mechanism behind this ability has remained elusive. In recent years, researchers have proposed that quantum mechanics might hold the key to understanding how birds navigate using the Earth's magnetic field. The leading hypothesis involves a protein in the bird's eye called cryptochrome. Cryptochrome is a light-sensitive molecule that plays a role in the bird's circadian rhythms, but it is also thought to be involved in magnetoreception. When light strikes cryptochrome, it triggers a chemical reaction that produces a pair of entangled electrons. These electrons are in a quantum superposition of spin states, meaning that they can exist in multiple spin configurations at once. The hypothesis suggests that the Earth's magnetic field interacts with these entangled electrons, influencing their spin states. The bird's brain is then able to detect changes in the spin states of the electrons, providing the bird with information about the direction and strength of the magnetic field. In essence, the bird's navigation system may rely on a quantum compass, where the entangled electrons respond to the magnetic environment in a way that allows the bird to orient itself. While this quantum compass hypothesis is still under investigation, it represents one of the most exciting possibilities in quantum biology. If true, it would mean that birds and potentially other animals have evolved to use quantum entanglement as part of their sensory systems. This would be a remarkable example of how quantum mechanics, typically confined to the microscopic realm, can influence large-scale biological processes. Another area where quantum mechanics might play a role in biology is the sense of smell. Traditionally, the sense of smell has been explained by the lock and key model, in which odorant molecules fit into specific receptors in the nose, triggering a signal that is interpreted as a particular scent. However, this classical model has been unable to fully explain the sensitivity and selectivity of the human sense of smell. An alternative theory, known as the vibrational theory of smell, suggests that quantum mechanics could be involved in the detection of odors. According to this theory, the receptors in the nose are not just detecting the shape of odorant molecules, but are also sensitive to the vibrational frequencies of the molecules. In other words, the receptors may be detecting the quantum vibrations of the molecules, much like a spectroscope detects the vibrational frequencies of atoms and molecules. One way this could happen is through a process called quantum tunneling. When an odorant molecule binds to a receptor in the nose, it could trigger an electron to tunnel through the receptor, provided that the vibrational frequency of the molecule matches the energy required for the electron to tunnel. This would create a quantum signal that allows the brain to perceive the scent. While the vibrational theory of smell remains controversial, some experimental evidence supports the idea that quantum mechanics might play a role in olfaction. For example, experiments have shown that humans can distinguish between odorant molecules that have the same shape but different vibrational frequencies, suggesting that smell is more involved in the process of smell. It would mean that quantum mechanics is at work in yet another area of biology, influencing our ability to detect and distinguish scents in ways that classical physics cannot fully explain. The vibrational theory of smell adds yet another layer of complexity to our understanding of sensory perception. It suggests that our noses are not simply detecting molecular shapes, but are tuned into the quantum vibrations of molecules, allowing us to perceive subtle differences in scent. This idea pushes the boundaries of what we thought was possible in biology, and if confirmed, it would provide further evidence that life has evolved to harness the strange and powerful laws of the quantum world. Are our minds quantum? Perhaps the most speculative and controversial idea in quantum biology is the notion that quantum mechanics might play a role in consciousness itself. Could the strange and mysterious phenomena of the quantum world, superposition, entanglement, and tunneling, be involved in the processes that give rise to our conscious experience? This idea was first proposed in the 1990s by physicist Roger Penrose and anesthesiologist Stuart Hameroff, who developed the theory of orchestrated objective reduction, or ORC-OR. According to their theory, consciousness arises from quantum processes taking place inside the microtubules of brain cells. Microtubules are tiny tube-like structures that provide support and shape to cells, but Penrose and Hameroff propose that they also serve as the site of quantum computations that give rise to conscious thought. In the ORC-OR model, quantum superpositions form in the microtubules, allowing the brain to process information in a way that classical computers cannot. These quantum superpositions remain in place until they undergo objective reduction or collapse, resulting in a conscious experience. According to Penrose and Hameroff, this process of quantum collapse is not random, but is influenced by the underlying geometry of space-time itself. In other words, consciousness may be connected to the very fabric of the universe at the quantum level. While the ORC-OR theory is fascinating, it remains highly speculative, and there is currently no experimental evidence to support the idea that quantum processes are involved in consciousness. Critics argue that the brain is too warm and wet for delicate quantum phenomena to persist for any meaningful length of time. Quantum superpositions and entanglement are easily disrupted by interactions with the environment, a process known as decoherence, and the complex, warm environment of the brain would seem to make sustained quantum coherence unlikely. However, recent research has suggested that biological systems, including photosynthetic complexes and enzymes, may have evolved ways to maintain quantum coherence in warm environments. If these findings hold up, it raises the intriguing possibility that the brain could also harness quantum mechanics in ways we have yet to fully understand. Some researchers have even proposed that quantum mechanics might play a role in the mysterious phenomenon of free will, suggesting that the inherent indeterminacy of quantum events could provide a mechanism for conscious decision-making. Quantum biology is still in its infancy, but it has the potential to revolutionize our understanding of life at the most fundamental level. If quantum mechanics is involved in processes like photosynthesis, enzyme catalysis, bird navigation, and even consciousness. It suggests that life has evolved to exploit the strange and powerful laws of the quantum world. This raises profound questions about the nature of life itself and whether quantum mechanics might be essential for the emergence of living systems. One of the most exciting aspects of quantum biology is its potential to inspire new technologies. By studying how nature uses quantum mechanics to achieve remarkable efficiencies and sensitivities, we may be able to develop new quantum technologies for use in fields like energy, medicine, and computing. For example, understanding quantum coherence in photosynthesis could lead to the development of more efficient solar cells, while insights into quantum tunneling in enzymes could lead to the design of new catalysts for industrial processes. Quantum biology also has implications for the search for life beyond Earth. If quantum mechanics plays a fundamental role in life, it suggests that life might be more common in the universe than we previously thought. Just as life on Earth has evolved to harness quantum mechanics, life on other planets or moons could have developed similar quantum processes to survive and thrive in their environments. The discovery of quantum biology on Earth may provide clues to where and how we should search for life in the cosmos. Quantum biology is a bold and exciting field that challenges our classical understanding of life. It suggests that the strange and counterintuitive phenomena of the quantum world, superposition, entanglement, and tunneling, might be at work within living organisms, allowing them to perform tasks with incredible efficiency and precision. From photosynthesis to bird navigation, and perhaps even to the processes of consciousness, quantum biology offers a glimpse into a hidden world where life and quantum mechanics are deeply intertwined. While much of quantum biology remains speculative, the discoveries made so far hint at a future where we understand life at a deeper, more fundamental level. As we continue to explore the quantum world, we may find that life has evolved to use quantum mechanics in ways we never imagined, revealing new insights into both the nature of life and the universe itself. In the next chapter, we'll explore one of the most fundamental and mysterious aspects of quantum mechanics: quantum gravity. How do quantum mechanics and general relativity, the theory that describes gravity, fit together? Could the strange phenomena of the quantum world hold the key to understanding the fabric of space-time itself? Join us as we dive into the quest for a unified theory of quantum gravity, and the mysteries of the cosmos. As we've explored throughout this journey, quantum mechanics and general relativity are two pillars of modern physics that offer powerful insights into the workings of the universe. Quantum mechanics reveals the strange and counterintuitive behaviors of particles at the smallest scales, while general relativity describes how gravity shapes the large-scale structure of space-time. But when these two theories meet in extreme environments, such as black holes or the very early universe, they clash in ways that challenge our understanding of the cosmos. Quantum gravity aims to resolve this clash and provide a unified framework that can describe both the quantum and cosmic scales. But could a theory of quantum gravity do more than just reconcile these two domains? Could it help us answer some of the most profound mysteries of the universe, such as the nature of dark matter and dark energy, the expansion of the universe, and the possibility of a multiverse? In this chapter, we'll explore how quantum gravity might offer new insights into these cosmic mysteries and transform our understanding of the universe. One of the greatest mysteries in astrophysics is the existence of dark matter, a mysterious form of matter that makes up roughly 85% of the matter in the universe, yet has never been directly observed. Dark matter doesn't interact with light or any other form of electromagnetic radiation, which makes it invisible to telescopes. We only know it exists because of its gravitational effects on visible matter, such as galaxies and galaxy clusters. Since dark matter doesn't emit, absorb, or reflect light, traditional particle physics has struggled to identify its nature. But some physicists believe that quantum gravity could hold the key to understanding dark matter. In particular, certain theories of quantum gravity predict the existence of new particles or fields that could account for the missing mass in the universe. One of the leading candidates for dark matter is a hypothetical particle known as the axion. Axions are incredibly light particles that are predicted by certain extensions of the standard model of particle physics, as well as by some theories of quantum gravity, such as string theory. Axions could interact with gravity, but not with light, making them an ideal candidate for dark matter. Another possibility is that dark matter is made up of primordial black holes that formed in the early universe shortly after the Big Bang. According to this idea, quantum fluctuations in the early universe could have led to the formation of small black holes, which would now exist as relics from that time. These black holes would be nearly impossible to detect directly, but their gravitational effects could account for the presence of dark matter. Quantum gravity could also offer insights into how dark matter interacts with space-time. Some researchers have proposed that dark matter is not made up of particles at all, but is instead a manifestation of quantum effects in the structure of space-time itself. In this view, dark matter could arise from the way quantum gravity modifies the fabric of space-time on cosmic scales, leading to the gravitational effects we observe. If quantum gravity can explain the nature of dark matter, it would provide a breakthrough in our understanding of the universe's composition and structure. It would also open up new possibilities for detecting dark matter, perhaps through experiments designed to probe the quantum nature of gravity. Another major puzzle in cosmology is the existence of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Dark energy makes up about 70% of the total energy density of the universe, but like dark matter, it cannot be observed directly. Its presence is inferred from the observation that galaxies are moving away from each other at an accelerating rate, suggesting that some unknown force is counteracting the pull of gravity on large scales. The nature of dark energy is one of the biggest unsolved questions in physics, and it may be related to the quantum properties of space-time itself. One possibility is that dark energy arises from the quantum vacuum, the lowest energy state of the universe, which is filled with fluctuating quantum fields. According to quantum field theory, even empty space is not truly empty, but is instead a seething cauldron of virtual particles that constantly pop in and out of existence. These fluctuations could create a small, positive energy density that exerts a repulsive force on the universe, causing it to expand. This idea is known as vacuum energy, and it is one of the leading explanations for dark energy. However, there is a major problem with this explanation. The predicted value of the vacuum energy density from quantum field theory is vastly larger than the observed value of dark energy, by a factor of about 10 to the power of 120. This discrepancy, known as the cosmological constant problem, is one of the greatest mysteries in theoretical physics. Some researchers believe that quantum gravity could provide a solution to the cosmological constant problem. In particular, certain approaches to quantum gravity, such as string theory, suggest that the vacuum energy could be fine-tuned by the quantum properties of space-time. This could lead to a small but positive value for the cosmological constant, which would explain the observed acceleration of the universe's expansion. Another possibility is that dark energy is not related to the vacuum energy at all, but is instead a manifestation of a new quantum field that permeates the universe. This field, sometimes called a quintessence field, would evolve over time, leading to the observed acceleration of the universe. The behavior of this field could be governed by the principles of quantum gravity, offering a new perspective on the nature of dark energy. Whatever the true nature of dark energy may be, understanding its quantum origins could provide profound insights into the fate of the universe. If the expansion of the universe continues to accelerate, it could lead to a future scenario known as the Big Freeze, in which galaxies drift apart, stars burn out, and the universe becomes a cold, dark, and lifeless expanse. Alternatively, if dark energy evolves in unexpected ways, it could lead to a big rip where space-time itself is torn apart by the accelerating expansion. One of the most exciting areas where quantum gravity could make an impact is in our understanding of the early universe. According to the Big Bang theory, the universe began as a hot, dense singularity about 13.8 billion years ago and has been expanding ever since. However, the Big Bang theory breaks down when we try to describe the universe at the very first moments after the Big Bang, where quantum mechanics and general relativity both come into play. In the moments immediately after the Big Bang, the universe was incredibly small and dense, with temperatures and energy density so high that the classical description of space-time provided by general relativity no longer applies. Instead, we need a theory of quantum gravity to describe the behavior of the universe at these extreme conditions. Understanding the quantum nature of space-time during this period could provide insights into the origins of the universe and the fundamental nature of reality. One of the leading theories of the early universe is cosmic inflation, which suggests that the universe underwent a rapid expansion in the first tiny fraction of a second after the Big Bang. This inflationary phase smoothed out the initial irregularities in the universe and set the stage for the formation of galaxies and large-scale structures. Inflation is supported by observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, which shows that the universe is remarkably uniform on large scales. However, the exact mechanism that drove inflation remains unknown, and quantum gravity could provide the answer. Some theories suggest that inflation was driven by a quantum field that interacted with the fabric of spacetime, causing the universe to expand exponentially. Understanding the quantum origins of inflation could also shed light on the nature of the initial singularity, the point from which the universe is thought to have emerged. In some approaches to quantum gravity, such as loop quantum gravity, the Big Bang singularity is replaced by a quantum bounce, in which the universe contracts to a minimum size before expanding again. This idea, known as the Big Bounce, suggests that the universe did not begin with a singularity, but is instead part of a cyclical process of contraction and expansion. If this is the case, it could mean that our universe is just one phase in an eternal cycle of cosmic rebirths, with quantum gravity governing the transitions between these phases. The concept of a multiverse, a vast collection of parallel universes, each with its own physical laws and constants, has captured the imagination of both scientists and the public. But could quantum gravity provide the key to understanding the multiverse? In some versions of quantum gravity, particularly those based on string theory, the existence of a multiverse is a natural consequence of the theory. String theory predicts the existence of many different possible configurations of space-time, each corresponding to a different set of physical laws. These configurations, or vacua, could give rise to different universes within the multiverse, each with its own unique properties. The idea of a multiverse is also supported by the theory of eternal inflation, which suggests that inflation is not a one-time event, but an ongoing process that gives rise to new bubble universes. In this scenario, our universe is just one bubble in a vast, inflating sea of other universes. Each bubble could have its own physical constants, and some universes might be hospitable to life, while others are not. If the multiverse exists, it would have profound implications for our understanding of the universe. It would mean that our universe is not unique, but is just one of countless other universes, each with its own version of reality. Quantum gravity could provide the framework for understanding how these universes are connected and how they interact, if at all. The multiverse also raises deep philosophical questions about the nature of reality and the role of observation in quantum mechanics. In the many worlds interpretation of quantum mechanics, every quantum event leads to the creation of new universes, with each possible outcome of the event occurring in a different universe. This suggests that the multiverse is not just a theoretical construct, but is a direct consequence of the probabilistic nature of quantum mechanics. The quest for quantum gravity is not just about reconciling two theories of physics, it's about understanding the fundamental nature of the universe. From the mysteries of dark matter and dark energy, to the origins of the universe and the possibility of a multiverse, quantum gravity has the potential to transform our understanding of the cosmos in ways we can barely imagine. While we are still far from a complete theory of quantum gravity, the progress made so far offers tantalizing glimpses of the future. Whether through string theory, loop quantum gravity, or other approaches, the discovery of quantum gravity would revolutionize our understanding of space, time, and reality itself. It would provide the key to unlocking the deepest mysteries of the universe and open up new possibilities for exploring the quantum nature of the cosmos. In the final chapter, we will explore the implications of quantum mechanics for the future of human exploration. Quantum mechanics has transformed our understanding of the universe in profound and surprising ways. From the counterintuitive behavior of particles to the mysteries of space-time, quantum theory has shown us that reality is far stranger than we could have ever imagined. But quantum mechanics is not just a theory for the abstract realms of particles and forces. It has the potential to revolutionize the future of human exploration, technology, and even our understanding of time and space. In this final chapter, we'll explore how the principles of quantum mechanics might shape the future of humanity. Could quantum technologies enable us to explore the stars, communicate across vast distances, or even travel through time? Could quantum computing unlock the secrets of the universe and solve problems that classical computers could never hope to tackle? And how might our understanding of reality itself change as we continue to unravel the mysteries of the quantum world? One of the most exciting and promising applications of quantum mechanics is the field of quantum computing. Traditional computers, like the one you're using to read this, process information in binary form, using bits that represent either 0 or 1. Quantum computers, on the other hand, use quantum bits, or qubits, which can exist in a superposition of both 0 and 1 at the same time. This allows quantum computers to process vast amounts of information simultaneously, making them exponentially more powerful than classical computers for certain types of problems. Quantum computers have the potential to revolutionize fields like cryptography, materials science, and drug discovery. Because of their ability to perform complex calculations in parallel, quantum computers could break the encryption codes that protect our digital communications, solve complex optimization problems, and simulate the behavior of molecules with unprecedented accuracy. But quantum computing could also have profound implications for our understanding of the universe. For example, simulating quantum systems is one of the most difficult tasks for classical computers, as the number of variables involved increases exponentially with the size of the system. Quantum computers, however, are naturally suited to simulating other quantum systems, such as the behavior of particles and fields at the smallest scales. This could allow physicists to model the behavior of quantum gravity, explore the early moments of the universe, and unlock the secrets of dark matter and dark energy. In a more speculative vein, Some researchers have proposed that advanced quantum computers could be used to simulate entire universes, including the laws of physics that govern them. If quantum mechanics allows us to simulate reality itself, it raises profound philosophical questions about the nature of existence. Could we, ourselves, be living in a simulation created by a super-advanced quantum computer? This idea, known as the simulation hypothesis, has captured the imagination of scientists and philosophers alike, and quantum computing brings us one step closer to exploring its implications. One of the most mind-boggling aspects of quantum mechanics is the phenomenon of quantum entanglement. When two particles become entangled, their quantum states become linked, so that a change in one particle's state instantly affects the other particle, no matter how far apart they are. Quantum entanglement has profound implications for the future of communication. In theory, entangled particles could be used to transmit information instantaneously across vast distances, even between distant star systems. This idea, known as quantum communication, could allow us to send messages faster than the speed of light, bypassing the limitations imposed by classical physics. While we are still far from achieving practical quantum communication on an interstellar scale, researchers have already made significant progress in developing quantum communication technologies here on Earth. In 2017, China launched the world's first quantum communication satellite, MICEUS, which successfully demonstrated the transmission of entangled particles between Earth and space. This achievement marked a major milestone in the development of secure quantum communication networks, which could one day replace classical encryption methods and enable faster, more secure communication. Quantum communication could also play a key role in the exploration of distant planets and star systems. Imagine a future in which we send probes to explore distant exoplanets, equipped with quantum communication devices that allow them to send data back to Earth instantaneously. This would enable real-time communication across vast distances, making interstellar exploration far more feasible than it is today. While faster-than-light communication remains speculative, quantum communication offers a tantalizing glimpse of the possibilities that quantum mechanics could unlock. As we continue to develop quantum technologies, we may find new and unexpected ways to connect with the universe and each other. The idea of teleportation has long been a staple of science fiction, but quantum mechanics offers a real-life version of this concept, known as quantum teleportation. Unlike the fictional depictions of teleportation, where entire objects or people are transported instantaneously from one place to another, quantum teleportation involves the transfer of quantum information rather than matter. Quantum teleportation relies on the phenomenon of quantum entanglement. When two particles are entangled, the quantum state of one particle can be transferred to the other particle, even if they are far apart. In this process, the quantum state of the first particle is destroyed and recreated in the second particle, effectively teleporting the quantum information from one location to another. While quantum teleportation has been experimentally demonstrated with particles like photons and atoms, we are still a long way from teleporting larger objects, let alone humans. The process of quantum teleportation is currently limited by the need for entangled particles to be physically transported between locations, and the complexity of the quantum states involved makes teleporting large objects extremely challenging. However, the principles of quantum teleportation could one day lead to revolutionary advancements in communication and computing. Quantum teleportation could be used to transfer information between quantum computers, enabling them to work together in ways that classical computers cannot. It could also allow for the creation of ultra-secure communication networks, where information is transmitted instantaneously and cannot be intercepted or tampered with. In the distant future, it's not impossible to imagine that quantum teleportation could be used for travel, at least on a small scale. While teleporting humans may remain the stuff of science fiction, teleporting quantum information across vast distances could open up new possibilities for exploration and communication, allowing us to traverse the universe in ways we can barely imagine today. If quantum mechanics challenges our understanding of space and matter, it also raises profound questions about the nature of time. Could the strange phenomena of the quantum world, such as superposition and entanglement, offer clues to the possibility of time travel? In classical physics, time is treated as a continuous, unidirectional flow, moving from the past to the future. But in quantum mechanics, time behaves in ways that defy our classical intuition. Quantum particles can exist in superpositions of different states, which means they can evolve in multiple ways simultaneously. In some interpretations of quantum mechanics, time is not a fixed linear progression, but is instead an emergent property that arises from the interactions of quantum particles. One of the most intriguing possibilities in quantum mechanics is the concept of retrocausality, which suggests that events in the future can influence events in the past. This idea is still highly speculative, but it challenges our conventional understanding of causality and raises the possibility that time travel could be possible at the quantum level. Another approach to quantum time travel comes from the study of closed time-like curves, CTCs, which are hypothetical paths through space-time that allow an object to return to its own past. Some researchers have proposed that quantum mechanics could allow for the existence of CTCs and that particles could travel along these curves without violating the laws of physics. In 2010, researchers at the University of Queensland conducted an experiment in which they simulated quantum particles traveling through CTCs. The results suggested that quantum mechanics could resolve the paradoxes typically associated with time travel, such as the grandfather paradox, in which a time traveler prevents their own existence by altering the past. According to quantum mechanics, the particles in the experiment behaved in ways that allowed them to avoid these paradoxes, offering a potential glimpse into how quantum time travel might work. While time travel remains speculative, the principles of quantum mechanics suggest that the universe may be far more flexible in its treatment of time than we once thought. Whether through retrocausality, CTCs, or other quantum phenomena, the possibility of time travel offers one of the most exciting and perplexing frontiers for future exploration. As we've explored throughout this journey, quantum mechanics has the potential to transform our understanding of the universe in ways that are both profound and unsettling. From the behavior of particles and forces to the nature of space, time, and consciousness, quantum mechanics challenges us to rethink everything we thought we knew about reality. The future of quantum exploration is bright. With advances in quantum computing, communication, and teleportation, we are poised to enter a new era of scientific discovery and technological innovation. But quantum mechanics also invites us to explore deeper philosophical questions about the nature of existence itself. Could the universe be a hologram? Are we living in a multiverse? Is time an illusion? These questions remind us that the universe is far more mysterious and complex than we can currently comprehend. As we continue to push the boundaries of our understanding, we must remain open to the possibility that reality itself may be stranger than we ever imagined. As we look to the future, the potential of quantum mechanics to revolutionize human exploration, technology, and understanding is truly limitless. Quantum computers could unlock the secrets of the universe. Quantum communication could connect us across the stars, and quantum teleportation and time travel could open new frontiers for exploration. But perhaps the most profound possibility of all is that quantum mechanics will fundamentally change our perception of reality itself. As we develop quantum technologies and explore the quantum universe, we may come to realize that our classical understanding of space, time, and matter is just the tip of the iceberg. The future of humanity in a quantum universe is one filled with promise, mystery, and awe. Will we one day harness the full potential of quantum mechanics to explore the stars, communicate across vast distances, or even travel through time? Only time and further discoveries will tell. But one thing is certain: quantum mechanics has opened the door to a new frontier in human understanding, and the journey has only just begun. As we venture into this quantum future, we are reminded that the universe is an endless source of wonder and discovery. With each new breakthrough, we come one step closer to unraveling the hidden secrets of the cosmos and our place within it. The future is quantum, and it promises to be more extraordinary than we can possibly imagine.